It's the further adventures of the LM111, 211, 311 comparator series. Why would you want to use one of these instead of a basic op-amp comparator? I'm Professor Fiore, and I'll explain it to you right now. First things first, dedicated comparators have certain advantages over using a general purpose op-amp as a comparator. What might those advantages be? Well, first off, fast switching times. You'll see these dedicated comparators switching between high and low output states much more quickly than a standard op-amp like a 741 or even second generation faster op-amps like a TL071, an LF351, something in that line. The output circuitry is also much more flexible, and we'll look at that in just a sec. But basically, these things will typically use open collector and or open emitter outputs. So the levels, your logic levels on the output end, are not tied to the power supply rails the way they would be in a normal op-amp comparator. In other words, if you had, let's just throw out a 741, for example, running on plus and minus 15 volts, you know that the comparator outputs are going to be just under that 15 volts. So you're going to be maybe 13.5 volts plus or minus. But, you know, a couple of diode drops, just a little saturation, if you will, beyond what the power supply rails happen to be. So interfacing that to a logic circuit can sometimes be a bit of a mess. You know, not a huge pain, but it is something you have to consider. Maybe you have to put in some kind of limiting diode or something along that line to tie that down, to bring it down to the logic levels, right? For example, a 0 to 5. With a dedicated comparator, the output is flexible enough that you can set those voltages, in other words, what constitutes the logic high and the logic low, separate from the power supplies. Right? So it's much more flexible as far as the interface between the analog side of the comparator, in other words, where you're picking up something like a sensor, and the digital logic output side of the comparator, right? Where you're going to drive the rest of the digital circuitry. Very often, these dedicated comparators have a strobe input. Typically, when you set the strobe input pin low, and that would typically be done through a little transistor. You would drive the base, saturate it, drive the collector down, to logic low, to ground. That nullifies the output. In other words, regardless of whatever the input is, the output of the comparator goes into an off state. And there are applications for that, for that kind of thing. What I'm going to do here is just look specifically, as I mentioned at the outset, at the LM111 series. So you've got the 111, the 211, and the 311. They're basically the same comparator, but as the number goes up, right, 1, 2, 3, the specs get a little bit looser. So you could think of the LM311 as sort of the commercial spec version. The LM111 would be, an aerospace defense kind of spec, all right? There is also a dual version of this chip. For the 111, it would be called the LM119, and for the 311, it would be the 319. So you get two of those in one IC. And that can be very handy for certain kinds of circuits. For example, a window comparator might use 2 op-amps. So you could implement that with a single chip, in this case, something like a 319. So let's just take a very quick look at the equivalent circuit. Now, if you look at this device from different manufacturers, and I have to say, this series has been around for decades. It's a classic chip in that regard. You will see slightly different versions of the input circuit because there's the original version, there are improved versions. This particular version that I'm showing up here is from onsemi. One cool thing about onsemi, they're like the E.E. Cummings of electronics companies. Everything's lowercase, It's not capital O. It's all lowercase on semi. In any case, this is their version of the 311. And if we look at the input end, we see a differential amplifier. There's some clamping diodes over here to prevent the inputs being too large and destroying the device. Biasing back up here with a balance. The strobe input's also over here. We go through a high gain stage out here. There's more biasing, all well and good. But here's the really cool thing is this output end. And if you look at typical op amp, what you see out here is a Class B push-pull, directly coupled, but a Class B push-pull output. Clearly, that's not what this is. As a matter of fact, if we look off the collector, there's no tie back. In other words, we would need to put in a pull-up resistor out here. This is an open collector output. So externally, we'll have a resistor going up to a power supply, which may or may not be VCC, and that's what makes this thing a little bit more flexible, and I'll give you an example of this shortly. And we also see a similar kind of thing down here off the emitter. You can tie that to something other than ground. They call pin 1 ground, but as you'll see, it doesn't really have to be ground. It's your logic low. If you want to think of it as logic ground in quotes, I guess you could think of it that way. But really, this is sort of a unique thing. Now, as far as output drive, this is much more capable than something like a 741 or a 351, a TL071, a 318 for that matter. You're looking at about a 50 volt max swing on the output and about a 50 milliamp drive current. So that's much larger than your average run-of-the-mill op amp. The switching times on this, it depends on exactly what the overdrive is, the load, a few other things, but you could be looking down in the, hundreds of nanoseconds, possibly quicker than that. So, again, compared to those op amps, this is going to be a pretty quick circuit. So let's take a look at this. You will notice that the schematic symbol is a little bit different than your run-of-the-mill op amp. And before I go any further, don't expect to find this under your basic semiconductors tab. You're not going to see it in here. You're not going to find it under op amps. And in Tina TI, you're going to have to go to Spice Macros and then look for comparators. So you click on here and you'll see the LM111. Bring it down here, off you go. So the odd looking thing here is, you've got what looks like a normal op amp triangle, plus and minus power supplies, plus and minus input signal, output, but then you got this little bubble, and then there's a transistor sticking out here. Like, what the heck is going on? Well, the bubble is a carryover from digital logic. A bubble on an input or an output means invert. In other words, when I look at this as an ordinary comparator like I would with an op amp, if the output is high, think of it as logic high, the bubble inverts that, so now it's logic low. And then I use whatever that signal is, the high or low, to simply drive this output transistor. And you notice that, it shows pin 7 and 1 here is not being connected to anything. I have to connect this to the outside world. So what I've done here very simply is I've tacked on some plus and minus 9 volt power supplies. So, if you want to experiment with this on your, home system, you just need a couple of 9 volt batteries, but you have a wide latitude, and you could run this on plus and minus 5. You could run it on 0 and 5. You could run it on plus and minus 15, plus and minus 12. You have, you could run it from 0 to 15, your choice, a lot of latitude here. All right. But I'm just going to use a plus and minus 9 because I just want to throw in a nice AC signal. So the signal I'm going to throw in here is a 6 volt peak sine wave running at 1 kilohertz. That's just going to go into the non-inverting input. And then I have a potentiometer that's connected between the plus and minus 9 volt power supplies. So this tap, I can set this to get different potentials to compare against. Now, right now, let's see, we have it on 40%. So that means we're 10% off of 50. Let's see, so that should be about 1.8 volts because we'd be 10% down, 1.8 volts off of here. All right, so just shy of 2 volts, okay? whenever the input signal goes beyond that, or underneath it, however you want to look at that, we're going to get a state change out here, right? So if that's sitting at 1.8 volts and this sine wave coming in is negative or positive but low, in other words, half a volt, a volt and a half, then we're going to have a low output. Otherwise, we're going to have a high output. Now, if we have a high output, then at this juncture in our little schematic, that high would be turned into a low because of the bubble, and then a low drives this transistor off, right? So there's no current flow, which means there's no drop across R1 over here, which is our pull-up resistor. So the collector would be sitting at our logic level of 9 volts. Now, I've just happened to throw this in as the same power supply that I'm using, but I don't have to, and I'll show you that in just a sec. On the other hand, if the negative input was larger, so let's say the negative, the negative input sitting here at the reference at 1.8 volts, and my input signal is, -5 or something like that, then the output goes negative, but the bubble inverts that, so that's a high. Now you put a high voltage on the base emitter, end result, you turn the transistor on, current flows, it goes into saturation, in other words, and we drive the output low. So low in this case is going to be, a VCE sat above whatever you've tied the emitter to. So maybe 0.2 of a volt, right? 1/10 of a volt, 0.2, somewhere around there, okay? All right, now, before I go any further, this particular SPICE macro does not include the strobe pin. But remember, if you drag the strobe pin low, it just disables the output goes low. No matter what's happening on the input, the output goes low. In any case, let's do a quick transient analysis and you can see what's going on here. Okay, so we are going to need a legend. There we go. And I am going to change the color of this because those two greens are kind of close. So let's try, what do we got? Let's try blue. Oh, that's so much nicer. Okay. All right. So this kind of olive green, kind of bleh looking color, that's our 6-volt peak sine wave coming in. The maroon is the reference voltage that we're tapping off the potentiometer, right? So I said that's, about 1.8 volts. So each of these larger hash marks in here is 1 volt, and then the little ones are 0.2, right? So that's one little hash mark below 2, so this is 1.8 volts. And we can see, as we would expect, as the input signal goes positive, because that's on the non-inverting input, the output changes state, right? We can see this is sitting down here at, around 0.2 of a volt, right? That's the low. And then, boom, it pops up and it's coming right up to 9 volts. Beautiful. That's exactly what I expect. Now, here's where it gets fun, because just looking at this, it's like, well, okay, I can do that with, standard op amp. Yeah, you can. But let's say you want to drive TTL logic. Now you're going to have to come up with some kind of interface circuit for your op amp. Here, all you have to do is tie the pull-up resistor to your logic power supply, the 5-volt power supply, right? So this, like I said, doesn't have to be the same as these power supplies out here. So I come in and I say, let's do a transient analysis again. And hey, look at this. All right, so once again, right, there's our output, which is the green, that more Kelly green. And I'll just to be consistent, I'll change it back to blue. Right, and what do we see? That saturation is occurring right at 5 volts. In other words, it's right at the logic voltage that we're using here. Got 3.3 volt logic? Well, you could use that too. Just change this, and that's going to give you your high level. We can see that the low level is still sitting, like I said, as a VCE sat, in other words, a couple tenths of a volt. Right, so you compare those two. Right, just set that automatically. Beautiful. You got to love it. All right, but as I said, it's even more flexible than that. We can do weird things over here. So let's take this emitter, instead of bringing the emitter to ground, let's just, for fun, because why not, right? Let's bring that over to my negative power supply, all right? So the emitter is now sitting at minus 9 volts, all right? Now what happens? All right, here's my logic level. Change it back to blue again. I need a macro that just changes colors to blue. There's our 5 volts for the logic high, and our logic low is down here at, roughly 9 volts. So, man, again, what if you wanted to do this with a plain old op amp? Trying to set these levels. I'm not saying it's impossible to do, but it's an extra thing you have to throw into the circuit. Here, you just have to decide, well, this is the potential that I want. And if you're saying, well, geez, you happen to use this power supply. Yeah, I only used it because it was already there, but I could certainly have another power supply or a voltage divider or something along that line, to connect the emitter up to. Same sort of thing off the collector, all right? Now, that's not all you can do with this, of course, because it is ultimately a high-gain differential amplifier. I mean, that's the front end of this thing. You can add other components and make things like oscillators. You can make square wave oscillators and, again, have the ability to control these potentials, right? Feed that square wave into an integrator, and you can get yourself a triangle wave. Right, so it's a versatile little chip, right? In fact, and I haven't tried this, so I can't vouch for how well it works, but if you look up the applications in the data sheet, they even show Class D amplifiers using these comparators. I mean, why not? As long as it's a fast comparator, you have enough current to drive, power transistors, power FETs. Yeah, sure, you could do that. I can imagine that. All right, pretty cool chip, I think, overall. It's been around for a long time, but, it's still useful. They're inexpensive. It's a great little hobbyist chip. Okay, till next time, this is Professor Fiore saying, take care, have a good one.